All right. Hi, everyone. I'm Brad Baker, and I'm going to talk today about a paper that I've been looking at that's related to stuff that I've been working on for over 4 years now, I would say, on the distributed information bottleneck and how it can help us study complex systems, which we certainly do work with here at the Trent Center. Let's go ahead and dive into it. Let's motivate what we're doing here. So, complex systems. Let me hide this thing first. Will it go away after a while? Okay, cool. So complex systems, what are they? Any system where you have individual agents or pieces or parts of the system that are operating in tandem with one another, interacting in complex ways, that's a complex system. It's a broad, often quite qualitative word used to describe various kinds of systems. There are variants of that, complex adaptive systems that vary over time and adapt to change, the feedback loops and that kind of things. And any complex system is tough for people to analyze, right? We look at a bunch of ants, and we're like, that's basically chaos. Nothing's going on there. But actually, they're all interacting in complex ways and creating, this hive mind and interacting. Similarly, neurons. If I looked at a bunch of neurons, spiking a time series, I would have no clue what I'm looking at. But we use, computational algorithms and informational tools to actually make large-scale inferences about these systems. So that's what the largest motivation behind this work today. But there's a specific problem that falls within that. It's actually called the CEO problem in practice, but I reframed it to call it the postdoc problem. I don't know if David's here because I include him as one of the postdocs, because he usually does come. Yeah. So the idea is that Sergey wants to know some time series. Like he wants to know the exact perfect value of this time series. And he's like, okay, I've got 4 postdocs. Go and give me information about this time series. We all look at it and have differently distorted views of this individual time series data. Maybe it's, whatever we're looking at. We're each looking at some piece of, different piece of brain data, there's different kinds of noise, whatever you want to call it. The idea is that we as the postdocs cannot communicate with each other, and we also can't get information from Sergey about what he gets from us. So we're kind of just dealing only with our imperfect data. And we also have a rate-limited channel. So if you're like me and you communicate with Sergey, you have a rate limit of 1 million Slack messages per day. You just message him constantly and annoy the hell out of him. Or maybe you're more reasonable and just send 10 to 20 to 30, stuff like that. And the idea is that Sergey is trying to reconstruct the signal in the best way possible with these communication-limited channels that each have imperfect information. And the information bottleneck is going to give us a distributed information bottleneck in particular is going to give us a mechanism to look at that, where we have different systems that have partial information about the entire complete system, and they're all coming in to one kind of aggregator or one overall system that we're interpreting it with, and we want to make correct inferences about that entire system. Right?
You want to talk about
information. What was that?
Talk about over one channel overwhelming everyone else.
Well, that's a problem. That can also be a problem. Yeah. Yeah, if you have like asymmetry in the channels, this problem is it's a big problem in information theory, actually called the CEO problem. If you research the paper, I've linked it up here, and you can look at it in more detail. This paper came out in '95, and there's been a lot of work dealing with it. And one thing that we can do is we can, we have these also very complex machine learning models, deep learning models that we can apply to our data. And we hope that applying these models, better than just giving us some predictive output with some certain amount of accuracy, or in the case of LLM, some desirable behavior, and human replicability and stuff like that. We want to be able to make inferences about the larger system that we're pulsing into our model by looking at the model itself and what it's learning. And this is essentially one of the goals of model introspection, right? Is you're trying to make inferences about the system you're analyzing by looking at, the weights, saliencies, and post-hoc stuff like that don't always get you there. But that's one of the goals of model introspection. A lot of the time is to explain the system that you're actually applying the model to. And that's one thing that we'll be exploring in particular for this kind of work is, application of deep learning models to complex systems and how they can be then used to make inferences about these systems. So let's do some background. So basic probability theory, for those who either haven't taken it or have not taken it in many, many years. Probability distribution. So for a continuous variable, it's just a continuous function defined over a domain, and it has to be integrable, this other properties. what we'll be dealing with is discrete probability functions. So the probability mass function, which is the equivalent for discrete variables. And the big rule that you'll encounter in elementary school probability is that they have to sum to 1, right? That's the only restriction. But still, this function p of x can be any function. And there's a question how you determine that and how you measure that. And that usually comes down to either discretely sampling from your data. You measure your data and try to build up some idea of what the distribution looks like. You might have a model for what that distribution is. You might be a Bayesian and do something completely different. But there are a lot of ways to model that distribution. But I'm leaving that up for debate or up for future work. Another method to make sure you have under your belt: joint conditional probabilities. You can condition a probability distribution on another variable. So if I know some information about a variable B, I can then condition the distribution of the variable A on that variable B, and it'll change the shape of the distribution based on the information from B. I also have joint probability distributions, like in this picture here, where you're looking at joint events that are happening simultaneously is usually one of the intuitions, and you're looking at this 2-dimensional cloud now, or 3 dimensions, 4 dimensions, whatever, however many variables you have. And just reminders about some of the standard identities that you encounter in basic probability. The definition of what a conditional probability is, just the joint probability divided by one of the probabilities that you're, the probability that you're conditioning on. The chain rule as well, which is a way of breaking up joint probability distributions. And Bayes' theorem, which is kind of a combination of these other two things that I just described, but it gives us a way to move between conditional probabilities. So that's just basic stuff that you will have hopefully seen. Now for the information theory stuff. So information theory is a broad field. There's a lot of stuff that they do within it. At the large point of information theory, when it was first invented by Shannon and all the people that were talking about this stuff back in the day, was to look at communication channels and to look at uncertainty and loss of information in these communication channels. Entropy is a mathematical concept that quantifies this idea of uncertainty within a communication channel of some kind. Really, it can be any kind of variable, any random. So a discrete random variable x, and pardon the weird formatting as I converted everything to LaTeX, that has a probability mass function. Some p, either we can count the probabilities and build that function again, or we know it's Gaussian or something like that. It's just defined in this way. You take the logarithm, usually you use phase 2 logarithm if you're writing your entropy in bits, but you can do it a lot of different ways as well. And the intuition behind what entropy is, right, is that higher entropy in your signal indicates more uncertainty. How I've had it described to me is the higher entropy, the more surprised you will be by the data you look at. Chaotic systems are often high entropy systems, for example, that change and fluctuate with, highly based on the initial conditions, that kind of stuff. There's a simple numerical example as well for certain kinds of simple problems, like flipping 2 points in a row. You get a binomial distribution, stuff that plays quite nicely with the logarithm, and you get these really nice identities for just computing the entropy. So that's what entropy is. Any quick questions about what entropy is and what it describes, how it's computed? It's quite straightforward, actually, I think. All right, cool. We can extend entropy from one variable to multiple variables, both by conditioning and with joint probability. So this is just extends exactly what we did with the joint probability distributions and conditional probability distributions. So we could have the joint probability that you're just marginalizing over each variable with the joint probability distributions. And then with the conditional entropy, you're doing the same thing. Can someone tell me why this works on the right-hand side, what the difference is? And it's just based on one of the definitions that I went over quickly in one of the slides. So the one difference is that you're dividing by p of x, right? And what is that? What is that? P of x and y divided by p of x? What definition is that?
Base rule.
What was that?
Base rule.
It's the conditional probability distribution definition. So it does.
So that's what Bayes came up with. The rest is due to another.
It's all interwoven. It all is interwoven. Yeah, but this is just using the definition of the conditional probability distribution. Right. Mutual information. So mutual information, intuitively, it's the reduction in the uncertainty of a variable given information about another variable. So oftentimes you'll hear mutual information kind of described like as a distance function. That's not really works, right? So information theory is essentially a probability-based field. It is, you're talking about probability distributions, you're talking about uncertainty, and it's a reduction in that uncertainty in particular. So you would expect to see, lower or higher mutual information if y and x reduce one another's uncertainty. And so there are a few identities that can be used to compute the mutual information. So H here is the entropy. I should have defined that in the previous slides. But you can define the mutual information by subtracting the entropy of one variable by the conditional entropy of that variable conditioned on the second variable. That's one way to compute it. There are a bunch of different identities. And here's just the unraveling of that equation here. You can, as an exercise, if you want to just write all these things out, it's actually quite simple to do a lot of the algebra to get these identities.
People don't like algebra. They think they can get away without it.
No, you need to do it. It's like I've done it. I've derived these equations, I think, 4 times in different classes because it's actually very simple once you do it. But it looks like it's like, how did you get that equation? Well, it's just algebra at the end of the day. Because you have these definitions of what the entropy is, you can just plug them in, do some algebra, move some things around, and you get this definition here on the right of what the mutual information is. And here's a nice graphic, I think, that describes the relationship between all of our entropy measures and our mutual information as well. So mutual information here sits right in the middle, using the conditional probability and the conditional entropy and one of the individual entropies. And then we have the joint entropy as of course, the entropy of both, and the individual entropies overlapping there. All right, so cool. Any questions about mutual information? Very quick. There's a lot of detail. There's a lot of analysis and stuff you can do with mutual information, a lot of other stuff, but I'm just going to leave it at that. Say that again? It's not symmetric. Yeah, good call. All right. So one thing about information theory that I am a big stickler about that Vince has gotten mad at me for is that estimating mutual information and other other information theoretic quantities is an imperfect science unless you know the distribution of your variable. If you know the distribution perfectly, or you have infinite samples, then you can estimate these quantities with small, tiny amounts of error.
Let me step on Vince's side just for a tiny bit. Nearest neighbor estimators.
It works okay. Yeah.
There are non-parametric ways that break in when you don't have enough samples,
right.
You get negative values and stuff, but they are asymptotically correct. And they're non-parametric. You don't have to know anything.
Yeah.
But yeah.
So there are a lot of ways to estimate these, based on what you know about your variables and don't. This flow chart is very nice. And then there's the new thing in deep learning as well is to use variational methods, which work quite well for for estimating a lot of these quantities using tail divergence and stuff. And I'll talk about that in a second. So let's move on to the meat of this presentation, the information bottleneck. What is it intuitively? Imagine you have a long message. Palpatine's giving a speech about Darth Pelagius the Wise or whatever that he gives in the Senate episode. Was that episode 2 that he does that? Or episode 3, I think. I can't remember. And Anakin Skywalker here is the bottleneck with his limited critical thinking skills. He doesn't entirely grok, that Palpatine is actually an evil dude. Spoilers for a Star Wars movie that's been out for over 20 years. So he's taking this really long message and compressing it down to the idea, well, it's probably okay if I go and murder all my Jedi friends and do all this terrible stuff, And so the idea is you have a really long message, and you have a finite channel to communicate it upon, right? And then you are then trying to reconstruct the content of that message with that finite communication channel. And you end up with, and that is the information bottleneck, the size of this channel intuitively. So looking at the map, it exactly encodes that idea. So you're now looking at the mutual information between a compressed representation U. So we just defined U as some function of f of x that is compressing x in some way. So we're losing information. Typically, you don't expand it. Impossible to do, in fact. And you are looking at the mutual information between that compressed representation x and the compressed representation in y, and the trade-off between those two. And the beta parameter is controlling the strength of that bottleneck. So as you increase the bottleneck, if you increase this beta parameter, you're going to be overemphasizing the encoding, the mutual information between the features x, the input, and this compressed representation. As you decrease beta, so as beta goes to 0, you'll be emphasizing the term on the right, the information between the compressed representation and y. So if we're thinking about x and y as features and labels, which we will be in a second, that's kind of how the information bottleneck is working mathematically. So that's just the construction of the information bottleneck as a measure, not a proper measure theory measure, but whatever. Any questions about that? This has been around for a few decades now. Tishby has written so this comes from a guy named Naftali Tishby. from out in Israel, and he has done a lot of research about this trade-off in physical systems and communication systems and stuff like that. He's come to some really bizarre conclusions as a result of it, as I'll talk about in a second. But this idea is quite powerful, right? That you can talk about an input representation, a smaller compressed representation, and reconstructing some labels or an output representation, and that trade-off in terms of the size of this this compressed representation and how you're compressing either the features or trying to represent the label space. Does that track for everyone?
So this measure could be negative sometimes?
Yeah, beta 0 it would be negative if as long as the mutual information is positive, you're estimating it correctly, right? It should always be positive, but
So, Brad, can you hear me?
Yeah.
Okay.
Yes.
So, is this an estimate? Is information bottleneck this is an estimation of an actual parameter of, for example, the probability, the distribution of U, or
It's
is
not
it a
the-
metric? Is it an empirical method that we decided is good for something to do, or is it an actual thing?
So I think I'll try to answer your question this way. So it is a quantity that you can measure, right? Not about the probability distribution of U so much, but about the trade-off between using U to represent the information. Using U to represent the information in X and using U to represent the information in Y, right? Because you have this input, you have this output, and you have this compressed channel in between, and you're just looking at that trade-off between that compression and decompression within that bottleneck. That's all that this quantity is measuring, and it's used. I'll talk about how it can be used in a little bit. So one thing you can do with it is you can just throw it into a variational model and use it as a regularizer. So if U was a set of layers in a deep neural network, you could trade off how those layers in the deep neural network are representing the input versus how they are representing the output. Does that make sense, Ashkan?
Yeah. So, continuing that question, I got that. But based on U, for example, can someone argue the relationship between mutual information of U and X and the mutual information of U and Y is not linear? Because essentially what I'm saying is that sometimes it's BI of UX minus I U of Y powered by 2, for example, something like that.
Yeah, I mean, I think
Can't we argue that based on U, this formula can sometimes should change?
Yeah, so that's a very interesting question. I wonder, so this would go back to like Tishby's really early work on physical systems. I wonder if they've encountered that at all. But that's a good point, right? So you could potentially have a non-linear trade-off here between.
I'm right to say that this model assumes that the relationship between the two mutual information is linear, right? That's a correct assumption. Okay.
Yeah, so that's the assumption here. But that's an interesting thing to dig into, actually. I want to think about that more now that you bring it up.
Okay, thank you.
Yeah, and I've mentioned, as I said, mutual information is often quite difficult to estimate in practice. One of the things that people have done to work around this is using the KL divergence, right? Which is used in variational learning for years and years now to estimate mutual information and similar quantities. So this is just, very quickly, I'm just linking to this deep variational information bottleneck paper, which the big contribution is that they just reframe this trade-off using the KL divergence and the expected value here for. So here okay, let's look at the different. Yeah, unfortunately, I didn't define R here in the slide. Let me recall what that is. Right. I don't even define it in the paper. I didn't go closely into the variational bottleneck paper, but if you want to dig more into the variational approaches, I'm kind of skimming over it because I think we can just talk about the distributed IB stuff in a moment. But the long and short of it is that you can use the same variational representation that we use, for BAEs and stuff like that to do this, to measure this bottleneck. All right. So now, going back to applying this to within deep learning models. So as I described, when Ashkan asked this question, Tishby and some of his students have looked at since about 2015 is they're trying to use this idea to describe how deep neural networks are encoding whatever system that they are learning. So Tishby is not so much doing what this paper ultimately ends up doing in terms of looking at like interactions between input variables and stuff like that. But he was just looking kind of at a way to looking for a way to describe the learning dynamics during deep neural network training. This as we've said time and time again, the theory in deep learning is lacking, and people are still trying to come up with good mathematical explanations for how they learn and what they do. And his idea was, we have this, we have our input y, and the neural network is working as this compression channel, where it's trying to efficiently compress the representation in order to do something with the output y hat, right? So either you're using an autoencoder, or if you're doing some predictive problem, you're actually trying to encode information about features and how they're useful for predicting some variable. But that's the connection to deep learning. Does that track for people? So the idea, though, the expansion, though, is that instead of having one channel, we now have a set of layers, right, that are connected usually. So in their original paper, they just did it with MLPs, but it applies to CNNs as well, quite trivially, and to RNNs as well. I actually have a publication doing it with LSTMs. So it's not that hard to extend to other networks. But does that track? Is everyone kind of grokking? I see some ponderous spaces, some couple nods, maybe looks of boredom. I don't know. Not sure. All right. Well, we'll just move on here. In that case. One of the cool things that did come from this paper that I actually quite like that they did is they created this. It's sort of an introspection technique. It's not, I think, fully clear what it is. It's a bit still opaque and requires a lot of interpretation. But essentially, what they do is they model the mutual information between the hidden layers and the input, between the hidden layers and the output, right? So you're looking at these compression channels, and they do it for each layer in this network. So these are 4-layer networks, I believe. And they are just showing this change in the mutual information representation over time. This information plane representation, they connect it to the information bottleneck by saying that there is that these networks experience a trade-off in terms of compressing the data. So initially, I'll talk about the phases in a second. But this information plane thing is quite cool. You can just graph things in a 2-dimensional plane. You get some trajectories that look fairly consistent, and they do show some kind of interesting dynamics. And here they're showing 3 different networks trained on different portions of the data, and how the training dynamics differ in terms of compressing information between the hidden layers and the input, hidden layers and the output. That's just this information plane stuff. Connecting it more to information bottleneck. So what they proposed in these papers in 2015 and 2017 is that neural networks follow an information bottleneck principle during training all the time. They say that what happens during training is that the network will essentially first try to represent both the features and the labels in the within the hidden layers. Where you see this, like you'll see both things are increasing during the training period. At the output layers, things are already highly represented about the output, of course. And then what happens is you see this compression phase where the information around the labels remains high and actually continues to increase, but then the information around the features decreases. So this bottleneck actually changes during training. This is what they hypothesized.
What are these individual dots?
I think it's a neuron, and the different colors are different layers. Yeah. Yeah, and so this is also background for this distributed stuff, but it's important to kind of understand. So this was the very broad claim that Tishby and his student Schwartz-Div made in 2017. And Sachs, one of my favorite authors that I've talked about to no end in reading groups, did a very critical paper of this, basically saying, actually, no, it depends on the architecture of your network, particularly it depends on the style of activation function that you use. And you don't see anything that looks like real compression in these neural networks, just during training, which is what Schwartz-Div made these really broad claims that all networks follow this 2-phase encoding and compression scheme during training. Sachs says no. And it's quite funny because there was a lot of drama on the open review where Tishby's like, this paper attacks our work through the following flawed and misleading statements. And, they go through it and, Sachs has a really long response. Tishby has a part one, like a second response, like taking everything down, like being really critical. Sachs comes back, claps back again. Tishby says the authors don't know how to estimate mutual information correctly. We believe these facts nullify the arguments given in this paper altogether. It's hilarious to me to see this kind of drama between people. Like I've definitely gotten mad at people on open review, but you're always trying to be professional to some extent. It feels extremely non-professional.
Well, but that's when this happens all the time, only not all the time it gets us fixed.
Right. But the cool thing about this is that they got their paper accepted despite Tishby's very long diatribe saying that Sachs doesn't know how to estimate mutual information.
How did they estimate mutual information? Did they use how did they estimate the PDF for the X and Y?
So
did they estimate it or assume?
So in the original paper, Tishby and folks used a bin-based estimator, so just a histogram-based estimator. And I believe Sachs, they just used the same estimator. I don't know where this claim came from about them not knowing how to estimate the mutual information, because Schwartz did release their code base. I've used it. I assume Sachs used it. So it looks like the same code. I can't imagine that they do anything more sophisticated than that, or this is before the variational stuff even came out. So they're doing very simple estimators. So this is all background, right? And about the drama of Tishby and all the information bottleneck stuff. So the people kind of feel good about just kind of knowing what information bottleneck is talking about, the kind of the background with what Tishby used to talk about deep learning to some extent. And now we'll look at the distributed information bottleneck. And so in full transparency, I'll mostly talk about the methods. And then what I want to do is have us look at the results together and pull them apart together. I've looked at them, I'm familiar with them, but it'll be good to kind of pull apart what this thing is doing. Because the methods are actually quite simple. I think we've stepped step by step through the information bottleneck stuff. The distributed information bottleneck is, in my opinion, a trivial addition. But what they do experimentally is quite cool. Well, I don't think they would disagree. I think it's straightforward. I've talked to Kieran. I haven't said that to him, but Kieran, I love your work and I think it's extremely cool. Right. So the idea is that we are looking at these systems like in the CEO problem or the postdoc problem, as we had before, that have imperfect channels of communication, imperfect reads on whatever signal that they are trying to represent. The difference between the CEO problem to some extent is that we are looking at potentially different parts of a constituent signal. So we're looking at different parts of the system. So if we're thinking about like a circuit, we're looking at different points in the circuit, different entry points, maybe. If we're looking at a physical system with particles, we're looking at different groups of particles, different sizes of particles. If we're looking at the brain, we're looking at maybe different regions of the brain. I don't know. And the information bottleneck here is this trade-off in how you're representing the input. But now you're doing it for each subset of this larger system that you're looking at. So Tishby, they just take the input representation of the entire input space. So you're representing your entire input space with this smaller communication channel. Kieran and folks said, well, why are you doing that? Just break it up into smaller channels based on how your data is naturally decomposed or how the system decomposes naturally. And then you can look at how these parts of the system actually interact and how they trade off in terms of the information bottleneck quite differently. So this is the equation for the distributed information bottleneck. I think I might be missing
Brad,
here.
Sorry, before going, this question might be because I'm a little ignorant of how neural network works, but is this information bottleneck calculated for a specific weights based on the training set, or is it for the structure of that neural network? Because if you change the training sets, I assume this result will change, right?
Yes, yeah, absolutely. It'll change depending on the training set.
So it's only happened, this only works for the weights that you have trained, right? Only for that weight. It doesn't say anything about the architecture that you used.
Right. So Well, so yes, so Tishby did a bad thing, in my opinion, when he made these broad claims about how all neural networks on all kinds of inputs will have very similar dynamics during training. What Kieran does in this work is they move away from this introspection tool where they're looking at the weights, and they're more trying to disentangle the system, right? So they're pulling away from model introspection and now going more into analyzing the system itself, which I think is one of the cool things about this paper. So rather than looking at, just how the network is compressing the input, although you are still doing that, you're actually looking at interactions between different parts of the system that you're inputting into your model and seeing how they interact. And so there's a missing I here on the right, which I think I can add quite quickly here if I just make a quick edit. Oh, actually, no, I'm not missing it. Okay. So all that this is doing is, so you have now a compressed representation for each subset of your input. So a subset of features. I don't think it would work for a subset of samples necessarily. It depends. I mean, you could maybe think about it that way. How I always think about it is a subset of features. So if you have, again, like independent components in the brain, you're looking at how the model is representing each of those components independently from one another. And now Ashkan's question about nonlinear interactions, I think, becomes even more salient when you decompose the system like this. But we'll just leave that as an assumption for now, that this is that is now not only linear in terms of the mutual information between the input and output, but also between the it's linear between components, right? And so this contribution. Do you see now why I say it's quite simple? Like all they're doing is taking it and they're breaking it apart as a sum. I think Kieran would agree with me, like it's not that complicated. And then you're still representing the input with the joint compressed channel, or the output with the joint compressed channel.
Hey Brad, is I the component number?
Yes.
Yes. And this just follows from independence then.
Yes, exactly. So if you assume that xi are independent, then this will hold. But that's again an assumption, right? We could make more complicated distributed information bottlenecks with potentially nonlinear terms if you wanted, or interactions between the variables, but then it would grow in complexity. You'd have to think about other metrics as well.
All I meant to say is that if the components are independent, then I think you would get this.
Yeah.
You always would get a
So
sum.
I'm just using
It would
independent
never be
components.
not a sum.
Yeah. So if we have like independent components from Neuromark, for example, yeah, we would get this for free, right? This is just assumed.
But even
absolutely.
if it were nonlinear, it would still be a sum.
Right. Yes.
Okay.
Absolutely. Yeah, sum over I. Yes. Okay. So does everyone rock this? Are we all good about how this works? Breaking up the input now in terms of a subset of features or components, however you want to do it. I'm talking about components based on what people know here, but you can break it up in a lot of different ways. All right. Just another implementation note was that, so there's an issue, right, for continuous output Y, and typically what is done for these kind of variational information bottleneck approaches is you have to discretize the support of the variable, end up doing a classification problem. If you want a really good representation of your output, the classification is going to grow to be impossibly huge. So they just replace the normal variational loss with this info NCE loss, which is essentially like a rehashing of cross entropy, but with you can use another distance function other than what is standardly used in cross entropy as a replacement. So you don't have to sort of arbitrarily discretize your output space in order to create some arbitrarily large classification problem. That's just an implementation note. All right, now let's dig into these results. We have quite a bit of time, and I hope we can look more closely. Okay, so what they do in all these experiments is they train a network and they essentially force the network to fall under different bottleneck constraints. So Tishby was using the information bottleneck sort of as an interpretation mechanism. They say deep neural networks learn, we have this information plane, and the information bottleneck perfectly theoretically describes how all deep neural networks learn. Dax says no, and Kieran and folks then look at it and say, okay, well, we can still use the distributed information bottleneck and control that bottleneck. This is usually what most people do nowadays. They can artificially control it and see how it actually is changing how the model trains or how your input is represented, right? So let's look here at the circuit example. So they have here a Boolean circuit with 10 binary inputs connected with a few different gates or and or XOR gates. And they use the distributed information bottleneck to compress the training objective function, which I showed you before. And they sweep over different bottleneck strengths. Right. And so here they're showing the cross entropy error in black. Right. And then and they show that the information transmitted about each of the inputs, so this is each a different color here on this graph, measured through the KL divergence. You can show that it decreases heterogeneously as the bottleneck tightens, depending on which part of the circuit you're looking at. So it actually gives you, so if I just had this circuit and I didn't know the structure of the circuit, just by looking at the various inputs into the circuit, I can get heterogeneous information about how that circuit is composed by looking at this this information bottleneck. So what I kind of missed.
Sorry, Brad.
So,
I have a question about this. So you have to go through all possible combination of X to be able to say something about the system, right?
Right.
But you have a limited number of limited view of X. How can this information bottleneck, how can this figure say anything about that? Because it's only limited to based on the X that you've seen.
So that's a good question, and that's what I was just about to say. Was for this particular example, I have had trouble connecting the intuition with what we actually learned about this particular circuit. So did anyone else read the paper, or am I just no? Okay. So looking at this this circuit, so over the course of the sweep, schema approximations of the relationship between X and Y, you see different subsets of the input. Yeah, I also am not entirely clear on this particular example. I think the following,
because it goes against system theory and system engineering, right? For the reason that we can have a transfer function is because of linearity of the system, and you can you just can sweep different sinuses with different frequency and add them, and you are mathematically, it is proven that you have the system. But here, at least actually, I don't know.
I have an answer from the paper because I didn't read this part very closely for this example. I was more interested in the subsequent ones, but here's the answer in the paper. Okay, so the sweep over beta effectively sorts the input gates by their relevance, predicting the output bit Y. The best approximation, and this is just the second paragraph in the results section of the paper if you're looking at the paper. The sweep over beta, yeah, sorts the inputs by the relevance to predicting the output bit Y. The best approximation of the relationship between Xi and Y includes all 10 inputs. The next best discards inputs between X4 and X5. Essentially, an approximation involving only one input, X3, is found before all predictability of Y is lost. So let's maybe pull that apart a little bit. So they're looking at, so the best approximation is using all 10 inputs. So I think maybe what they're doing here, maybe I misunderstood, because I thought they were looking at all channels individually, but maybe they're looking at each channel, like adding each channel one at a time and combinations of the channels. So this next best channel is sorting the, see that? X4 and X5. Yeah, so they go on to say peering into the black box allows us to connect the approximations to the circuitry. X3 routes for the fewest gates to Y, making it particularly influential in determining the output. The next course's approximation to exist for a significant range of beta adds information from X6, X8, X9, and X10. These inputs all route through the same XOR gate latent circuit. Yeah, I'm still a little bit lost as to how that connection is made, but they seem to have some explanation here for it. They're only using the input-output pairs and the information bottleneck trade-off.
For this specific one, they can essentially sweep over all possible because x and x, all x are bits, right? It's a binary.
Yeah.
I mean, it doesn't even matter if it is not binary. That's or anyway. So you can essentially sweep over everything and map the whole thing. But I wonder for more complex thing. That's what 10 bits.
Yeah, so let's look at a more complex case, and one that intuitively I was able to track a little bit more. So I have the comment for this one pulled up as well that we can reference. But I quite like this approach because what they're doing is they're essentially looking at spatial decompositions of data, which we're very familiar with here in this lab. And they're looking at the relationship between color and an image. So this is RGB pixels, you're just looking at color information, and the spatial representation, projecting onto some, certain basis with different, directionality, right? And so they're looking at, so let's pull apart this caption here at the top. Right, so Da Vinci's painting of the Mona Lisa represents a specific relationship between the position of the frame X and the color Y. The position is decomposed in panel A into horizontal blue and vertical orange components for use with the distributed information bottleneck. And they display different approximations for increasing bottleneck strength. So from left to right, they're increasing the bottleneck in these images. Right, and they mark each bar in the plot. So the prediction for each position is a distribution over colors. And the color display is the one with maximum probability. So they're actually using a neural network to predict. I see. So they're using a neural network to predict the pixel in each location from the center. Instead of doing a full autoencoder, they're actually just predicting pixels at each location, and they're decomposing with this kind of spatial representation, vertical or horizontal, or they have this these more complicated basis sets here. This B1 is along 6 different axes, and then C is just a different schematic they don't really describe in detail. And then D is just the normal information bottleneck without any sort of spatial basis that it's placed upon. So I think that this example makes a bit more sense to me in terms of you're sweeping over sort of strength in terms of decomposing this image in different ways and forcing it to fall onto this basis. And then you're looking at so on this top row, you get a very nice summary of how colors are kind of distributed horizontally in the image, right? The top one, that's the easiest one to make sense of. And the next two are a little bit more complicated, but you get sort of broad blobs that are where the color is more or less following the image based on that spatial decomposition, right? So I think that this is quite cool. And I think that it's quite intuitive. I talked to Kieran about this example, and he said reviewers hated it for some reason. But I think it intuitively makes a lot more sense than the circuit-based example. And then the next example, which I have a lot of trouble interpreting, is the physical example. Yeah, how do people feel about this? Does this one kind of pass your judgment a little bit more quickly than the circuit one, maybe?
Not the same. Is one of them is 1D, the other one is 2D. That's not that much different. So
yeah, exactly.
Because both of them are discrete. One of them is 2D. This one is 2D. The other one is 1D. But it's
right. Yeah, it's a very similar approach. You're just with the image as well. You have a very nice, I think, spatial intuition in how you're decomposing the image. That's what I like about this example. All right. Well, people feel good about this. Let's try to tackle the much harder example, this physical system. So this one, I've looked at a few times, and I find it quite tough. So it's a distributed information bottleneck on gradually quenched glass, and they're looking so they're looking at particles in glass that is being quenched after melting or molten glass, right? So you're quenching glass. I believe is what they're doing here. They're looking at the local neighborhood around each particle is decomposed into 50 radial density values, structure functions for each of the large and small particle types. I'll pull up the comment here. We can kind of follow along. It's kind of tiny to read maybe on the screen. Yeah. classification task is to predict whether the center particle is the locus of an imminent rearrangement event. As in figures 2 and 3, the training error increases with the bottleneck strength. While beta is small, the training and validation cross-entropy errors display the hallmark behavior of overfitting. Increasing for beta for distributed IB acts as regularizer, which is quite common in the IB literature right now. You see variational information bottleneck is a regularization for a lot of problems. It closes the gap between the two errors by restricting information around the structure functions. Accuracy on the validation set is comparable with that of support vector machine training the same data until a majority of the structure functions have been compressed away. As beta increases further, classification accuracy grades until it drops precipitously, stopping briefly at an approximation scheme marked with the vertical gray bar. The information maintained about each of the structure functions over beta sweep from panel A for the smaller type A particles. So B is the information maintained about each of the structure functions over B over the beta sweep from panel A for the smaller type A particles. C is the same as panel B. Yeah, okay, we're just looking at each of the things here. So yeah, this I struggle to understand. So I imagine they're just, so these basis functions are just, this is just radial density function. That's probably something you get in like material science where you're looking at, you know, lattices and arrangement of particles and materials and stuff like that. But I'm not at all familiar. Does anyone have a background with that kind of stuff? Done anything with molecular systems and specifically structural systems? Yeah. But I think that it's quite similar to what they're doing with the Mona Lisa image. It's just that they have a different way of decomposing the data that's very specific to this kind of data, right? The structural radial basis functions. Yeah, so if I looked at this, and even I imagine if I knew a bit more, I don't know if I would have to be able to interpret it as readily. But let's see what they say in the text about this particular figure. Right. So they use it as a way to describe a relationship between static configurations and future rearrangements. Decompose into structure functions, we saw that. Okay, so they're just comparing different quench protocols here. So each of these panels are different quench protocols. So different sizes of particles. I don't find this too intuitive, other than describing the the classification accuracy of the model and using it as a regularizer. Potentially. Okay, so they say they learned something fundamental about these complex systems. They don't really describe what they actually learned. That frustrates me. So I think
it's interesting. They have broken it into based on their basis, right? It's like how you do Fourier transform. They have the spatial basis,
exactly.
And then based on that, essentially they've used the idea behind linear system identification here.
Yeah. I think it's interesting. I think there's a gap for me for explaining then what they do with that, as you described, and what this means for this particular system. And they don't go into it in the paper at all, which frustrates me. But yeah, I mean, I think it's an interesting approach. So I mean, we can think about it then. You know, how might this be useful in neuroimaging? So this is something. So Vince came across this paper. I mean, I've been working on the information bottleneck since MRN, but I only got into the distributed information bottleneck a couple of years ago, and we really haven't finished any project just because I've been busy with other stuff. But I think there are a lot of ways we can adapt this to thinking of the brain as a system. Whether or not we want to think and use our independent components as a set of basis functions, maybe for decomposing the signal, is one thought I had. But really, I think the more interesting thing is like using it to do something like spatial ICA, right, where we have a spatial decomposition that we're interested in. Maybe we also want to enforce some independence between that spatial decomposition, and we look at the trade-off in that bottleneck. Just on MRI without using any pre-computed set of components. I think I think that an ICA-like method using this bottleneck could make a lot of sense. And I just would need to finalize the details. Maybe Rogers, if that's something you'd be interested in thinking through, it would be something interesting to work out the details for and what it exactly would mean for neuroimaging data. Certainly beyond like spatial decompositions, you could do it for any other decomposition of interest in neuroimaging. But yeah, does anyone have any thoughts in how this might be adaptable for neuroimaging in particular? I mean, thinking about just the intuitive idea that you're breaking down your data into a set of features, a set of maybe spatial basis functions that are independent, just one idea. You could break it up in any number of ways though. So any thoughts, any ideas?
Can this be used to find, for example, optimal component number? Because you are
Maybe.
trying to find the bottleneck for the decomposition itself, right? Not the brain,
That's
right?
what
You want the decomposition bottleneck for decomposition itself, nothing about the brain.
That's kind of what I was thinking initially as well. Was you for some particular problem you would be able to find using this bottleneck in a network trained to predict some problem, you would be able to use the bottleneck to find the network that was most salient for that predictive problem. Most certainly, I think that's probably the first thing that we could do with this. Yeah, and then we could maybe think about if you want to come up with another decomposition. Yeah, again, it's whether it's saying something about the brain. I think it would be if it's depending on the predictive problem, and again with all the stipulations of what data you're working with, and estimators and all of that, and the assumptions going into we're not interacting between we're just using a linear interaction between the input and output representation. But yeah, I think it would say something under those assumptions, which are a lot of assumptions. But yeah, I mean, I think this is interesting. This has been on my to-do list to dig into this more for quite a long time, and I've taken efforts to initially start it, but just again, time is a thing. So if you know someone looking for a project, this has been on my projects list for years now. If you know someone looking for a project, or you just want to talk to me about it more and work on it, I would be more than happy to collaborate on it. I think it's I think we can come up with a couple interesting ideas to apply this method to neuroimaging analysis. Yeah, and I think it's could be more than one paper for sure. So, and yeah, any other further questions and discussions? We're almost right at the time, but we got a couple minutes before we have to head over and listen to Sergey talk about edge solutions for artificial intelligence.
And bottlenecks. Information bottlenecks as well.
Post-doc bottlenecks. Yeah.
Can you turn back the slide?
Yeah. Where?
Not. With the brain.
With the brains.
Yes.
Here.
As I understand, your idea is to use special components and find the bottlenecks between them, right?
Well, so that's what Ashkan was talking about as well. So the idea would be that we have like a decomposition already given to us, and we could just do some predictive tasks, whatever we want to do, brain age or diagnostic.
So my question is,
Yeah.
do you think we can use some time components, or probably even, for example, we can divide the recording on different parts?
If you did temporal ICA, you could. Yeah, so they would need to be independent, right? Would be the thing. Like Rogers was asking about earlier. So if you did spatial ICA, the time series are still correlated. It's the whole reason we can get DFNC or any FNC. So I think it would be problematic to look at the time series themselves in this way, maybe, because there would be interactions that we're not modeling. But if you did temporal ICA, certainly good, because then the temporal independent components would be independent.
Yeah, let's take questions online, offline.
All right.
Stop here. Thanks for everyone for listening. Next meeting is next door, and 9 cents.